1/3 times the absolute value of x. Okay. So now we have a fraction that's less than 1. Okay. So just like before, f of x equals 1/3 absolute value of x. You're going to get rid of any number that's not an exponent. Okay, so you're going to have f of x equals absolute value of x as your parent function. All right, so if we graph our absolute value of x again, we have our x and we have our y, and we have our absolute value of x. Okay, so we know here that c is equal to 1/3. C equals 1/3, so c is less than 1. So we know it's going to shrink vertically. And make sure I got enough space. That should be enough room. We have our x and we have our y, and we have a dotted outline as to where absolute value of x is. So this is our f of x equals absolute value of x. Okay. So remember, just like before, if you were to plug in x equals 1, y would equal 1. If you plugged in x equals 2, absolute value of 2 is 2, so y would equal 2, and so forth and so on and so on. Here, if you plug in 1, you have absolute value of 1 is 1, but that's multiplied by 1/3. 1 times 1/3 is 1/3. So instead of being 1, it'll be 1/3. So if you plug in 2, absolute value of 2 is 2, but you multiply that by 1/3, it's now 2/3. So instead of being 2, it's 2/3. So it's just a little higher up. If you plug in 3, you finally end up with 1. Okay, so instead of being like this, your graph is now like that. Okay, so it shrinks vertically. Okay, so this would be your f of x equals 1/3 absolute value of x. Okay, does that make sense? All right. Okay, any questions on this one? All right. Oh, I'll leave that up. Make sure everyone's done. All right. Okay, so now we're going to do what they call a test for symmetry. Okay, and symmetry is just like it says, across any x-axis or y-axis, it looks like a mirror image. So if you have a picture of it, you can kind of figure it out. But if you have just the function or the equation, you want to kind of take a certain number of steps. So let's say if we just give a quick explanation. So a graph has symmetry with respect to the y-axis if whenever any point on the graph is, or you can say equivalent to negative x comma y. So whenever you have an x value, your y value for that x value is the same y value for the negative x value. So let's say if we want to draw a quick example. Okay, so let's say f of x equals x squared. Excuse me. If you plug in 1 squared is 1, you get y equals 1. So you get 1 comma 1. Okay, so let's say if you plug in negative 1. Negative 1 times negative 1 is positive 1. So you get negative 1, 1. If you plug in 2, 2 times 2 is 4. So you end up with 2, 4. So if you plug in negative 2, negative 2 times negative 2 is 4. So you end up with negative 2, 4. So every x value and negative x value have the same y values. So this is symmetric across the y-axis. Okay. Or if you're just looking at a graph, it looks like it's almost like if you set a mirror right here, it just looks like a mirror image. Symmetric. With respect to the y-axis. Okay. Now if you have, let's say, a graph that has symmetry with respect to the x-axis, oh, didn't even need that if. Don't know why I put that. Whenever x comma y on the graph is equivalent to x comma negative y. Okay, so let's say, for example, instead of y equals x squared, let's say if we have x equal y squared, which is the same graph, the only difference is it's on its side. So x equals y squared. Okay. So here, if you plug in x equals 1, okay, that will be true for y equals 1 and y equals negative 1. So you have x equals 1, y equals 1 and negative 1 would be true for that one. Same thing with x equals 4. That's true for y equals 2 and y equals negative 2. So let's say 4 here, say 2 and negative 2, and it just keeps going like that. Okay, so this one is symmetric with respect to the x-axis. that make sense? All right. Okay, so now we're just going to have what they call a few tests for symmetry when you don't have the graph, but they just gave you a function. Oh, anyone's still writing? I'll leave it up there for a few more seconds. Ooh. All right. Symmetry, say even and odd functions. Okay, so to test to see if a function is even, okay, first thing you would do is replace x with negative x. Okay, and even is just the same as symmetric across y-axis. Okay. So if the function f of x is the same as f of negative x, then the function is symmetric across the y-axis. Or in this case, just even. All right, so let's say, for example, you wanted to test, I'll say test for symmetry. Across the y-axis, or just whether it's even. Say for problem A, you have f of x equals x squared plus 1. And let's say for problem B, you have f of x equals, let's say, pick a good one, x minus 2 squared. I'll leave it at x minus 2 squared. Okay, so say for problem A, you know the f of x is equal to x squared plus 1. And we know that f of negative x equals negative x squared plus 1. So all we did was replace every x with negative x. Okay. So we know negative x times negative x is positive x. So negative x squared is just positive x squared plus 1. Okay, so you can see there that they're the same. So since they're the same, it's symmetric across the y-axis. Or in this case, it's an even function. All right. Now, if we do problem B, we know that f of x equals x minus 2 squared. Kind of separate that a little bit. And we know that f of negative x, again, just replacing all the x's with negative x. So that's negative x minus 2 squared, which is just negative x minus 2 squared. Okay, so you know these two are not even. Not the same. So the function is not even. That means if you drew up or graphed f of x equals x minus 2 squared, it wouldn't look like a mirror image across the y-axis. Okay? But you don't have to graph it to see that. You just replace x with negative x, and if it turns out to be the exact same, then you know that it's symmetric. If it doesn't, then you know it's not symmetric or not even. Okay, so, I already did put not even. All right, so any questions on that one? All right. Oh, make sure to leave it up for a few more seconds. Okay. Okay. Now, what if you have what they call an odd function? An odd you would think would be symmetric across the x-axis, but it's not. It's actually symmetric across the origin. So I'll show you what I mean by that in a second. Is symmetric with respect to the origin if whenever x plus y, or x comma y, is on the graph, so is the point negative x, negative y. Okay, so if we were to draw up a graph of that, you have your x and you have your y. Let's say if you have this graph here, should look a little bit smoother than that, but okay. So if you have a point, let's call this 3, 5, then somewhere on the other side, you're going to have a negative 3, negative 5. So if you have a 2, 4, you'll have a negative 2, negative 4 on the other side. So if you wanted to look at the graph and say, wanted to know if it was odd, if you reflect it across the y-axis, and then again across the x-axis, it should be exactly the same. So if you got this one and flipped it here, so I'm trying to make sure I don't mess up the drawing too much. So if you flip it here, and then you flip it again, so if you flipped it there, and then you flip it again there, it ends up looking like that. So it's kind of a double flip with respect to the origin. Does that make sense, or did I confuse you on that one? Okay. I know usually that one's kind of hard to explain. All right, so let's say, this is called an odd function. Okay, so the test to see if a function is symmetric with respect to the origin or is an odd function. It's pretty similar to the one for symmetric across the y-axis. The only difference is you're going to replace both x and y with negative x and negative y and see if it turns out to be the same. Okay, so first you're going to replace x with negative x and y with negative y. Okay. Now, if you get the same function as f of x, then you know it's symmetric with respect to the y-axis. I mean, to the origin. Bless you. The same f of x function, then it is symmetric about the origin. Move that up a little bit. Okay, so let's say, for example, make sure everyone's done. Oh, leave it up there for a little while. All right. Okay, so let's say, for example, say test to see the graph of, where is it? Oops. Y equals x to the third minus x. Is symmetric across the origin. Okay. Quick note is that they may give it to you as f of x equals x to the third minus x. That's the exact same as saying y equals x to the third minus x. So if you get an f of x, all you have to do is change the f of x to y, and you're all set. Oh. Origin or odd function, same thing. Okay, so remember to test if this is odd. You're going to replace x with negative x and y with negative y. Okay, so we know we started off with y equals x to the third minus x. Okay, that's what we started with. So now we have negative y equals negative x cubed minus negative x. Okay, so all we did was replace the y with negative y and x's with negative x's. Okay, so we end up with negative y equals negative x times negative x times negative x is just negative x to the third. So we end up with negative x to the third. Negative times negative is positive, so we have plus x. But if we factor a negative out of those two, you have negative y equals negative x to the third minus x. So if we divide or multiply both sides by negative 1, the negatives cancel out. So we end up with y equals x to the third minus x. Okay, so they're both the same. Uh-oh, sorry. Does that make sense? All right, so we know that this is symmetric across the origin. So since they are the same, after replacing x with negative x and y with negative y, we see the functions are the same. Oh, I already said that. So the functions are symmetric with respect to the origin. Uh-oh. Or in this case, an odd function. Oh, sorry about that. All right, so any questions on that one? All right. Right. Okay. So now if you have a graph that is symmetric with respect to the x-axis,